Good morning, everyone. Welcome to the second day of the 2024 project meeting. Just doing a sound check for our online attendees. Can you hear and see us?
Yep, all good.
Thank you.
Okay, so good morning, everyone. So welcome to this first session of the day, which is dedicated to solar, heliospheric, and ionospheric science. So the first talk is going to be given by Rohit Sharma from the Indian Institute of Technology. He's going to give us an overview of the activities of the Solar Science Group from MWA. And just a note, because we have a single microphone here, the speakers will have to repeat the question from the audience and answer themselves because we cannot run with a mic into the room. Thank you.
Okay, yeah. Okay, thanks a lot. So I will be basically summarizing the updates from the heliophysics with MWA, and this is an effort of many people. And I'm just sort of like summarizing the stuff, the recent stuff mostly. Okay, so as always, we are sort of like driven by young people who are doing their PhDs. And in the workforce, we have like 4 PhD students, Soham, Pooja, Angelica, and Deepan, who contributed a lot for in the last couple of years. And Devajyoti and Surjit has been very instrumental in sort of like they're postdocs now, but they have been sort of like also working in sort of like making the project running within the collaborations. The recent works of areas, there are a lot of activity which is happening in terms of sort of like designing appropriate solar observations in general. So there have been a work related to, for example, the triggering of solar emission, especially for big flares, because they are the ones which is of sort of like a wider interest across the community. Then the solar imaging polarimetry, that is one of the novel things which have been occurring, and many of these topics are actually challenging the present notions in heliophysics, like the way we understand the fundamental processes which actually give rise to these phenomena. So Pooja is sort of like doing this type 2 studies, type 2 burst basically, and then the space weather aspects related to coronal mass ejection and basically heliospheric science using IPS and heliopolarimetry. And then, of course, the WinSkew, the evergreen topic with MW data is the detection of weak impulsive emission. So just to sort of like give a little motivation, the sun is very, very diverse in all aspects. So this is just a movie which basically is showing the solar rotation. This is a UV movie, and you can see there's a lot of activity which is happening at all scales. You can see like there are these small brightenings which are happening. There's a lot of activity in the loops. There are bright regions. There are not so bright regions, faint regions. They're called coronal holes, especially near the poles. predicting all this activity is really a non-trivial task. How do you basically know that there is going to be a burst, which or if a energetic phenomena which might be happening, so therefore designing solar observations from non-solar dedicated telescopes become a really challenge. The best bet is basically you maximize your allocated time coverage uniformly and try to hope for best, but that might not work always. And with the MWA, with the experience we have, is like it does not work most of the time. So we need to come up with a better strategy to, especially in sort of like scheduling these observations. And if we also then try to go the other way, where we basically see some counterparts in other wavelengths, for example, like let's say on the right we have this H alpha image, where you see the sunspots. So the more number of sunspots you have, the better the higher the activity will be. That may not also be true always. For example, like if there are big sunspots, they may not actually flare for coming whatever period of time on the period of which they are on the disk. And there could be like a small set of complex active region which might flare a lot. So there is unpredictability over which contribute. So this type of phenomena, they sort of like are make the solar burst prediction sort of like a unpredictable. And on top of that, these are just multi-wavelength. They are different wavelengths. So in radio, you will observe something else. These are you will mostly see some energetic particles, which again add to this particular complexity. So in overall, I want to basically say that, I mean, the unpredictable nature of solar events makes it really hard to predict scheduled observation in general. There have been attempts, like we try to do some attempts from let's say Gauss X-ray time curve, where you can actually get the sense of the activity level in real time, because then you can basically raise a trigger, and then we say that we want to observe with MWA. But it is not always. It is mostly actually does not work, simply for the reason that the X-rays and radio burst, so although they are sort of like very well correlated in strength, but may not be very well correlated in time. So radio burst can occur before, for example, the big events, and can occur after the big events also. So there is a sort of like a fine precision, which is a finite phase relay, which happens most of the time, which is very hard to sort of like predict. So over with 3,500 hours of MWA observation, we missed sort of like many events, basically with this type of approach. So we need to come up with a better strategy, and Deepan and Devjyoti were sort of like working on this triggering observation, solar observations. And this is for a general actually interest in general non-solar dedicated telescopes, where you would basically raise a trigger based on something which is substantial. And here the idea is basically to basically get a time series, or basically some kind of monitoring data and it should be sort of like in the same similar latitude longitudinal range, so that you are not very much different in sort of like in terms of the position of the source, the sun in the sky. And for that, the people, they have used this Yamagawa solar radio heliograph for this particular exercise, and the triggers will be raised depending on the real-time availability of this particular spectrograph, the data. So the strategy is basically so Yamagawa actually observes in a very, very wide range from 70 to 9 gigahertz or something like that. And it entirely covers the MWA band. And it actually gives you data in a near real time, not like exactly real time. So there is a sort of like a latency of, let's say, around 2 minutes of data. So if you are observing, let's say at whatever, 246, you will the latest data would be available, would correspond to 2 minutes before. This you can use this particular data and for basically computing the triggers. And MW actually MW works in this particular no capture mode, where actually the data which is prior to the current time is being stored in the buffer time. If the trigger is sort of like positive, then you can use this data and probably just dump it. And so this is basically the more or less the strategy. With this, you basically lose like a one minute of the data due to the latency. So the next is basically how do we basically create this trigger. So there is an example, and this has been working now, and we have actually acquired some radio burst using this particular technique. So this is the dynamic spectrum, the raw data, which you see in the panel 1 from the Yamagawa. And it has sort of like of course, there's a lot of RFI which one needs to take care of. So you basically do instrumental sort of like band pass and then try to remove it, remove the RFI, and then you basically get number 2 panel, where most of the RFI, especially at low frequency, is cleaned. And then you do some kind of binary dynamic spectrum, which is basically giving a threshold on the strength of the emission, about like 15 sigma. So that these number actually come from the Yamagawa sort of like the analysis experience. And then you basically say if they are sort of like clustered in an island, then you raise some kind of trigger. So these isolated islands would be rejected. For example, in panel 3, things like that will be sort of like will be rejected, and which are shown in sort of like green in the 4th panel. And the one which are sort of like clustered, which mostly would correspond to the radio burst, would basically raise a trigger. And with this, people, I mean, there is successful observations of some radio burst. In this, we would really want to thank Andrew for his keenness in scheduling all these observations, and so he was very instrumental in this particular effort. Right. So that was for the solar burst. And if we talk about like CMEs, for CMEs, the things are little relaxed. We do not probably want like minute to minute real time scale thing, because then CME is originating in the solar corona and then it is propagating, which takes a finite amount of time. And so basically one can sort of like raise this trigger at the hour scale or something like that. And there are already like these seed and cactus data, which is basically almost near time, and we can use these particular thing to schedule the observation. And you need to basically design your pointing very precisely in some way, because you want basically to capture the background sources. You don't want the solar emission as such. So you basically make sure that your sun is sort of like in the null of your beam. And this has been sort of like already operating. The second, one of the most exciting things which is happening is the detection of linear polarization. So linear polarization has been a challenge since the beginning, because the solar bursts produce a very weak signature in linear polarization, and the origins are not known, so it's a basically unknown problem. And there have been sort of like historically early detection results, which were sort of like looked very skeptically, like there could be because of the bad instrumentation effects and all. Apart from that, the linear polarization, which might be present, could get sort of like lost because of the high Faraday rotations that we observe in the coronal medium. So there was sort of like a sort of like an not very well motivated thing, but since there was some detection, so this is something which people were sort of like were attributing mostly to instrumental effects. And in fact, people were using it to constrain the instrument if you assume the linear polarization to be zero. But in the MW data, we got a little motivated because of finite Stokes Q in many of these bursts that we see. And from the first-hand calculation, it seemed that the instrumental leakages were sort of like not enough to explain such high levels of Stokes Q, and then Devjyoti, Soham, and Divya, they investigated this particular aspect in more detail, and then they come up with the imaging for this particular linearly polarized emission, and it is the first linearly polarized image actually which you get from MWA and later confirmed with GMRT observations. So interestingly, so this particular actually observation needs to be sort of like repeated again and again, and this will actually open a new horizon in basically interpretation of these radio sources which are associated with the active regions, why there is a linear polarization. So something needs to be asked there. And of course, all people were sort of like also using these Stokes Q and putting it zero by hand, which to compute Stokes V basically. But then those will also have biases on this, so those results needs to be checked again with respect to absolute precision. Then, of course, type 2 bursts. So type 2 bursts are very interesting phenomena which actually occurs in the solar corona, where these type 2 bursts are sort of like a drifting features in dynamic spectrum as a function of time. And these are mostly attributed to the shock propagation in the corona. And as shocks propagates outerwards in the corona, it sort of like drifts in the frequency space because the fundamental plasma frequency is changing as a function of height. And they appear in sort of like these bands. For example, like this H band is basically referred to as harmonic, and then the F is fundamental. And there could be multiple bands, and not just two bands. There have been observations with multiple bands, and mostly sort of like they are associated with CME. And recent observations with the polarimetry, you can actually constrain the magnetic field in these particular emission, which gives us information about the structure of the CME. Yeah, so there are some these studies which were performed for some events. So this is a type 2 burst, and the bottom panel shows you the location of various sources in different frequency, and the conventional notion here was basically the harmonic and the fundamental sources, they arise from a sort of like a similar sort of process. But the recent observations actually show that they might be associated with two different wavefront which are propagating in different directions altogether. So it could be a signature of sort of like multiple propagation or multiple sources which are sort of like propagating. And this is sort of like a new understanding in the origin of type 2 bursts. And this needs to be tested. So Pooja is currently doing these CME shock MHD simulations in collaboration with Nishtha. And they're trying to basically constrain the direction of the shock and try to test the hypothesis that these are indeed associated with two different type of wavefront. And so these are initial results, but this is something which is very interesting and challenges the common notion of type 2. Right. Then the coronal mass ejection. Coronal mass ejection is very fundamental in the understanding of space weather. And with MWA data, with the polarimetry, one can actually estimate, constrain the plasma properties inside this particular envelope of CME at different positions, right? So here's an example where you basically have the leading edge of the CME, which is marked in blue, and this particular right-hand side, the images of the Stokes circular polarization, basically. And you can actually make different PSF size regions and then try to obtain the spectrum for that. And then you do gyro synchrotron fitting for those. And it has been shown in previous studies that the more data you have, the better constraint it would be. Even if you have upper limits on the flux densities, you can actually do a better job in the fitting. But if you assume a very homogeneous source, it may not be a best approximation to constrain these parameters. So in this study, what they found was like a sort of like inhomogeneity needs to be an intrinsic part of this particular model to basically come up with a better fit results. Then this is the study which is associated with type 4 bursts, like type 2 bursts. Type 4 bursts are also thought conventionally to be associated with some kind of shock propagating in the solar corona, and they would basically appear as a drift. But a further analysis actually for this particular event actually shows us this is a pseudo drift. So there are actually two types of sources which are present at high and low frequencies, which are actually the similar type of sources, but occurring at two different times. And these sort of like are can be explained by basically the downflows of magnetic loops in the solar corona. So for example, like this is the image which actually shows you how does the source actually moves from higher up to really close to the flaring region. And this is sort of like an indication that these are trapped electrons in magnetic loops which are going down. And then we have the IPS studies. So IPS, if the CME is sort of like propagating in the interplanetary medium and you have background sources, you can actually measure the deflections in the and then try to basically get an estimate on the scintillation index, which gives you the plasma properties inside CME. So John Morgan and Angelina are basically working on this, and there is a follow-up talk on this. And last, mostly the WIN skew, which is basically the weak impulsive narrowband emission. So this we have talked a lot. But in what we are doing is at the moment we will be deploying this for the quiet sun phase data and try to basically get an estimate of this particular energy budget, which could give rise to such kind of like weak impulsive emission. Right. So I will basically say that, I mean, because we are reaching the maximum of the solar cycle, so this is one of the best times to really observe the sun. And I'll not talk about the gray line there because that's the prediction and it is not really performing up to the mark. But there is a lot of activity which is happening now, and solar observation from this particular period would be quite crucial to have. And actually, we actually had a campaign to track this monster called 13664 active region, and it was very associated with a very large sunspot. Actually, you can see in normal photograph images this particular spot. It produced like a variety of X-class flares. Like it was really literally saturating all the UV detectors and other stuff, and it produced like lot of CME. So this is sort of like a reprojected map of all the CME. All these blue curves are sort of like CME, and then this green poor little thing is our Earth, and it is sort of like bombarded by this particular CME, and it caused like lot of solar storms on Earth. And in fact, one of the cause for this Starlink thing was this particular period. And it also produces a nice aurora. So this is actually from Switzerland, the Jungfrau, and you can actually see the aurora here. This is and also produce the Australis, aurora australis, and then even at the smaller latitude at 26 degrees from Hanle in India, you could see the auroras which were produced during this. So yeah, so in and all work, there are a lot of progress in many science problems, and with better trigger-based scheduling, we will be actually saving a lot of data and also capturing the big events in a more effective way. And the focus is also on sort of like scaling our techniques because we have employed now a variety of techniques to basically input large amount of data, especially focusing on the archive. And of course, this will eventually lead to the development of some resources for SKLO in terms of like triggering and other stuff in analysis also. So yeah, I'll stop here.
Thank you. So we have time for a couple of questions. Yes, so yeah, we have to make the questions here.
Yeah.
Thanks very much. I have a question about your interpretation of the two different wavefronts for the type 2. So you have in the spectrogram that you showed, it's very similar. The structures are very similar, so that's why we think it's harmonics. But so would you not expect if you have two wavefronts that the signal in the radio spectrogram would be kind of different, or what would make it look exactly similar in the two bands?
Right. So so although I'm just yeah. So this particular just a second. Yeah. So you're referring to the dynamic spectrum for the type 2 bus, right? I guess.
Yeah, the one that you showed.
Yeah, this one. Yeah. Yeah. So this one is a sort of like a generic. This was not particularly the observation, but this one was sort of like a generic type 2 burst. But what we actually the interpretation, if you combine the information of the spatial position of these along with the dynamic spectrum, the frequencies, you can make out that the propagation direction or the orientation of the propagation is very different in both of these bands. And actually there could be multiple bands, which actually gives you even the third complexity, which the spatial position can. Of course, then one can argue that there is a sort of like a scattering effect which might be sort of like dominant, but the scattering effect would be sort of like more dominant towards the lower frequency than the higher one. Yeah, so I think Pooja is particularly working on that, so she would have more insight in this, I guess.
It's really good to see the bigger observation mode. I think that's really efficient. Historically, there have been an enormous number of solar observations during the daytime in order to catch the rare and interesting events. That does result in a lot of data in the archive that's not particularly useful. Do you have a plan to go back through all of the data and identify what can be deleted to help out with the archive considerations?
Right. So I would say that the data which is there for the quiet sun, that is also very interesting in its own respect. But certainly, like in some way, one can try to sort of like look for the ways to average it. For example, like the frequency averaging, like we probably would not require like fine frequency averaging for all of the data. Probably we can then sort of like make a sort of like a selection thing, like for which data do we want to basically try to do that. And that is something which probably we discuss most often during our meetings, how to downgrade sort of like the data that we have. Something to follow up on that.
We can move on to the second talk.
Sorry, I forgot to.
Thank you. Okay, so the second talk is going to be given by Ferry Lunter from the Curtin Institute of Radio Astronomy. And this will be about improving MWA ionospheric corrections using small satellites.
Yeah, sure. Turn around, give you a 5 minute. Actually, I should prefer. Is that good? Can everyone hear me? A bit higher up? Yeah. Better? Did I just hold it? Yeah, is that better? Yeah, okay. So good morning, everyone. My name's Ferry, and today I'm going to be talking about the work that we've done towards improving the ionospheric corrections using small satellites. Yeah. Okay, so I'll begin with a brief recap on the ionosphere and how it affects radio astronomy and the current limitations in the calibration, ionospheric calibration that we're aiming to resolve with this with our work. So the ionosphere. The ionosphere is an ionized layer of Earth's atmosphere, and because of this ionization, it contains a significant electron density. This electron density reduces the refractive index below unity, and this reduction in refractive index becomes significant below about 1 gigahertz. Now, this electron density is generated by solar radiation, and it's also impacted by both terrestrial and space weather, which means that it's inherently unpredictable both spatially and temporally, and therefore to account for or calibrate for these effects, you actually need measurement data. So as a result of this electron density, the ionosphere causes a number of unwanted corrupting effects to low frequency radio astronomy radio waves. These include phase path reduction, and that's manifests as a phase error or a phase shift. Now, this effect is directly proportional to the integral of the electron density along the path of propagation. We then have Faraday rotation, and this manifests as a rotation. Well, this is a rotation of the plane of polarization, manifests obviously as a polarization error. And this effect is dependent on the integral of the electron density combined with the Earth's geomagnetic field. And then we also have scintillation. Now, I won't talk too much about this today because I don't have time, but this is effectively small-scale ionospheric variability that causes some noise. So in recent times, we have had access to cost-feasible ionospheric measurement using global navigation satellite systems, such as GPS. Now, GPS is able to provide ionospheric electron density data in the form of a TEC estimate by using 2 frequencies and a differential phase measurement technique. And because of the use of circular polarization, ionospheric Faraday rotation actually also manifests as another phase shift for GPS. and therefore external geomagnetic model data is actually needed to disentangle the two effects and indirectly infer the ionospheric Faraday rotation to obtain a rotation measure estimate. And it's because of this indirect method of measurement, as well as the fact that ionospheric Faraday rotation is a much smaller effect, it's because of this that the uncertainty is actually quite high for rotation measure estimates. And in the context of polarimetry, this is a problem, and that's because MWA data, well, low frequency telescopes typically have to correct for polarization using ionospheric data from external sources. However, this high uncertainty and low inaccuracy or low accuracy is one of the current major limiting factors in polarimetry calibrations. For example, the currently available GNSS ionospheric measurement data doesn't actually provide a sufficient resolution to disentangle the ionospheric Faraday rotation from some classes of coronal mass ejection observations. To address this problem, we'd need a rotation measurement uncertainty about 15 milliradians per meter squared. So another problem is that the longer baselines of the MWA and future telescopes, of course, means that a completely different ionospheric condition is observed by each antenna station that comprises a baseline. And that means that the ionospheric phase and polarization can be many unknown multiples of 2 pi between the antenna stations. And ideally, absolute ionospheric measurement data is needed to calibrate for this. However, GNSS data is also not able to provide this because it itself is somewhat ambiguous. And also it doesn't provide, well, the uncertainty is too high, which means that at low frequency, at frequencies relative to low frequency radio astronomy, the uncertainty equates to many 2 pi phase or polarization rotations anyway. So small satellites present a new cost-effective opportunity to address this current limitation. And to this end, we have begun developing such a solution based on the 3U CubeSat platform. So in this talk, I'm going to talk basically about the 3 developments we've made so far. So that's a new remote sensing technique, small satellite antenna, and a transmitter. I'll then finish off with some of the future work that we're intending to do or have already started doing. So the first development was a new ionospheric measurement technique that addresses the Faraday rotation measurement limitations. And at the same time, it's also compatible with a 3U CubeSat. So the key enabling factor of this new technique is the use of linear polarization. Now, the key enabling factor is that linear polarization separates phase path reduction and ionospheric Faraday rotation into a phase shift and a rotation of the plane of polarization, respectively. This enables us to use differential phase measurement to independently provide a TEC estimate, and at the same time allows us to do differential polarization measurements to directly estimate the rotation measure. So this obviously enables us to directly measure, which is a huge advantage over GNSS, where it's an indirect measurement that relies on geomagnetic model data. The other key advantage of our technique is that both differential phase measurements and differential polarization measurements are dependent on TEC, which means that we can use simultaneous equations to disambiguate both measurements with fewer and lower frequencies than just using differential phase measurement. And this lends itself to 3U CubeSat or small satellite applications because fewer and lower frequencies means less transmit power, which means we have to use less power. So, and we found that to completely eliminate measurement ambiguity, we need 3 frequencies, which are compatible with small satellite amateur radio frequencies. It's 144.2 megahertz, 432.6, and 1297.8 megahertz. And when we compare this to conventional measurement techniques that use phase only, we can see we need 1 less frequency. We don't need the highest frequency. Now, recall that to address the polarimetry calibration challenges, we need a rotation measurement uncertainty of 15 milliradians per meter squared. Radians per meter squared. So to achieve this with a 3U CubeSat, we obviously first have to transmit simultaneously with the 3 frequencies, as we talked about before. And secondly, we have to have an orbital height of at least 1,000 kilometers, and that's just to make sure we measure the whole ionosphere, not that there's any electron density above our satellite. We also want to have a zenith angle coverage of at least 30 degrees, so that we're measuring a comparable portion of the sky to what the MWA sees. And then to ensure that we achieve the required rotation measure uncertainty, we need a transmit power of at least 0.1 watts, half a watt, and 1.4 watts for all 3 frequencies in ascending order. And we need this to overcome the receiver noise as well as the propagation loss between the satellite and the receiver. And the key here is that our technique only requires transmit power of a total of 2 watts, which is compatible with typical 3U CubeSat power budgets for scientific payloads. We also need an antenna gain. We have to ensure that this transmit power is radiated, translates to a sufficient radiated power with an antenna. And so we found that we need an antenna gain that's comparable with a dipole antenna. And this is also lends itself to 3U CubeSat applications because this is compatible with typical small satellite antennas at these frequencies, which are usually dipole antennas. And if you want to know more about this technique, you can have a look at the paper that's on the screen. Yeah. And the second development was an antenna design that meets the requirements we just showed you before. So because of the size constraints of the 3U CubeSat, our resulting design is a multi-frequency dipole antenna. So the 2 green elements you can see above the CubeSat body make up the radiating dipole structure. And if you have a look at the ellipses, the black ellipses, they are parallel resonant circuits that electrically shorten the antenna length. And then we've also modeled the solar panels and some other reflecting devices on the CubeSat body you can see on the right. So as you can see here, the antenna achieves the gain requirements at all 3 frequencies, up to a zenith angle of 50 degrees, in fact, which means this could be applicable to the SKA, which has an even larger zenith angle coverage. Yeah, so it achieves all 3. Yeah, and the last development that I'll briefly talk about is the RF payload, which obviously to achieve the requirements we introduced earlier. Now, this development was made necessary because of 2 unique challenges. Now, first of all, because of the transmit power requirements and the power budget, we had to have a transmitter efficiency of at least 50%, and that means a high efficiency design is necessary. However, our antenna design has an impedance that's far from the standard interfacing impedance. Now, I won't go too much into detail of this, but it effectively means that conventional high efficiency amplifier designs aren't compatible with this antenna. So a new high efficiency amplifier design was also necessary. And to address these challenges, we developed a new Class C amplifier design and a multiplexer design. And I don't really have time to talk too much in detail of these developments, but I'll just quickly go over the most interesting results. So we validated the new Class C amplifier design by prototyping an amplifier for the lowest frequency. And this was the frequency with the most non-ideal antenna impedance. So the measurement results show that we're able to achieve the required 100 milliwatts of transmit power whilst achieving the efficiency requirement of more than 50%, successfully validating the design. If you look at the graph on the rightmost graph, you can also see that our design actually satisfies the ITU out-of-band spurious emissions limits. And the reason why I point that out, I'll talk about in a second. And then we also validated the multiplexer with measurement results. So we just designed it for the 3 frequencies, the same 3 frequencies. And this was successfully validated with one slight discrepancy due to the layout of the circuit. And we then put this all together to develop the transmitter design. And our simulation results show that the power requirements for all 3 frequencies are met, whilst consuming less than the 4 watts, which we which was the power budget specified earlier. Yeah, and you can see more about this development in this paper if you'd like to have a look. And yeah, so that brings us to the end of my talk. The current future work we're working on is on the screen. The most interesting one to you guys might be the radio astronomy compliant high efficiency power amplifier for small satellite transmitters project that we've currently proposed. And this basically looks at, is the ITU out of band spurious emissions limit, is it actually enough for radio astronomy? And if it's not, how can we design a power amplifier that is good enough or has low enough emissions to be compatible with the future of radio astronomy? So you can imagine if there's thousands of these CubeSats up there, you kind of want to make sure they don't mess up your radio telescope. So yeah, thanks for listening.
We've got a question on mine.
Okay, so you have to read out on the mic.
Oh, do you want me to read it out?
Yeah, if you can read that. Sorry. Just hide that.
Yeah, so this is a question from Natasha. So she said, this might be, well, I'll skip that bit, but a 2-pi ambiguity only applies to a monochromatic case. As soon as you have multiple frequency channels, don't the baseline scale as lambda, but the ionosphere effect scale as lambda squared, so you can break the ambiguity? Yeah, that's the case for the telescope, but for the small satellite, it's not quite the case. So you need the 3 frequencies effectively, and that's common practice. You can avoid doing real-time absolute ionospheric measurement, which is effectively what some GPS satellites do, and that's by measuring the TEC along a certain period of time, and then you get sort of this bathtub scale as the GPS satellite goes across, but that's not real time. Real time needs multiple frequencies. Yeah, thank you. Yeah.
So it struck me that the measurement the thing that you need for ionospheric correction, that's 0.01 radians per meter squared. It's also sort of comparable to often you can get the best ionospheric model. Although those things are like model dependent, it will be more precise. So my point is that oftentimes using MWA data in the appropriate channel setup, you can get, say, for example, pulse rotation measures with a higher precision, like a 10 or order of magnitude better. And the ionospheric correction is obviously the limiting factor.
Yes, yeah.
Also, getting those precise rotation measures are scientifically interesting to study the ionospheric propagation effect of ions and models and things like that. So my question is that you said that your design approach is mainly driven by this particular number, and even without using the higher frequency, but is there a way you can improve that or push that further by using slightly better approach by using a higher frequency antenna for improving?
Yeah, so the question was, can the rotation measure uncertainty be improved further than what I showed? So can it be made better than 15 milliradians per meter squared? Yeah, so yes, of course it can be. You just need either more power, a higher gain antenna, a better receiver. There are many avenues you can explore, but it's definitely possible to improve. Now that 15 milliradians per meter squared, it's a relatively conservative number. It will, in fact, do better than that in most scenarios. Yeah. Thanks.
Thank you. So I think we can move now to the next photo.
Thanks.